All right, so we're going to start talking about section 6.6, which is solving exponential and logarithmic equations. So this continues our kind of philosophy of thinking of these as puzzles, because there's going to be sometimes more than one way to solve it, but usually one will be shorter than the other. So we're going to build up a couple of techniques to solve these, like bases for solving exponential equations, rewriting as logs to solve exponential equations using definition of log, using one-to-one property, and maybe doing some applied problems. So exponential equations are just hopefully what you would think that they are. They are equations that have variables in the exponent. Boom, done. So like 2 to the x equals 32, or 5 to the x plus 2 equals 4 to the 1 plus x minus x. Now, one of these we can solve pretty easily. We can solve this first one pretty easily, because we can look at this and say, okay, 2 to what power is 32? And we can say, okay, 2, 4, 8, 16, 32, that this is x equals 5. The other one's a little more complicated, so we're going to get to solve that one, but not just yet. To solve both of these, we really, we can solve the first one just by thinking about it, but really it would be easier if we got the variable out of the exponent. So one option here is to use what's called the base-exponent property. This does require the bases to be the same, so we can use that to solve 2 to the x equals 32, but not the 5 to the x plus 2 equals 4 to the 1 minus x. So long as our base is bigger than 0, of course, that's required for exponential equations, and our base is not equal to 1, then if we have b to the x equals b to the y, then that implies, or it follows then, that x equals y, that the exponents are the same. So 3 to the x equals 3 to the 5, we can hopefully look at this one and say, well, of course, x equals 5, right? And 4 to the x minus 1 equals 4 to the 8. Again, the bases are the same, so we can say, okay, well, the exponents have to be the same, so x minus 1 has to equal 8, so x is equal to 9. Not too bad. And then we can use that, of course, to solve, let's see, well, we could do it for here. For this 2 to the x equals 32, we could rewrite 32 as 2 to the 5, and then we see directly x has got to equal 5. Okay, so next slide. We have some more examples of this, right? So sometimes it's not going to be obvious that things are the same base, like this one, 3 to the 7x equals 27, but we can think of 27 as, oh, that's 3 times 9, right? And 9 is 3 times 3, so 27 is 3 to the 3rd, which means now I have the same base for both of these. So if my exponents are the same, the equation will be true. So 7x has got to be 3, and x has got to be 3/7. No problems there. So this one, 4 to the 3x minus 5 is equal to 16. We look at 16 and we say, hey, I know that 16 is 4 squared. And so then 3x minus 5 has got to equal 2, right? The exponents have to equal each other. And now it's just a plain old algebra problem, so I'll add 5 to both sides and divide by 3. Now, the nice thing with these, of course, is that we can verify that our answers are correct by graphing these things. All right, so we're going to do that. So we are going to, first off, put in two equations, right? So we're going to say y equals 4 to the 3x minus 5. And then we're going to say y equals 16. And we're going to have to zoom out. There we go. So we can see our intersection point here. We can use GeoGebra to do an intersection and click on my two graphs. And it's going to tell me that intersection point 2 1/3, otherwise known as 7/3, which is what we had gotten. All right. So So that's our base exponent property. Now this last one, 15 to the x equals 30, we can't solve it this way, right? Because 15 and 30 are two different numbers, so the bases are different. We can't rewrite 15 and 30 as some number to a power where it's the same number. So this one's not going to work. We're going to have to come up with a different idea. And that'll be the next video.